kiddos, so we're going to talk about the next kind of bonding. Next kind of bonding is called covalent bonding. So I'm going to write this down. You're also going to need your periodic table, so you should have that handy. All right, so bonding type number 2, covalent bonds. All right, so in ionic bonding, we said electrons were transferred. Covalent bonding, though, is when electrons are shared. All right, so you're going to copy this all down. Where there's a big space, there's going to be words revealed. So covalent bonding is when electrons are shared between nuclei. So I like to think of it as the atoms working together. They're cooperating. They're covalency. All right. So this happens, usually results when a nonmetal bonds with another nonmetal. So when a nonmetal and a nonmetal bond with each other. And if we think about the periodic table of the elements, we have this barrier, this like artificial barrier that we speak about, the staircase, and nonmetals exist on the right side of that periodic table. So our nonmetals will all be in this area. Plus hydrogen, which is all the way over here, but we know that hydrogen is a nonmetal. So hydrogen plus oxygen, nitrogen, fluorine, and all of the elements from group, 14 over. Bonds between two atoms of the same element are completely covalent. So when we have two atoms of the same element, I'm just going to put the examples down here. So, for example, hydrogen, when it bonds with another hydrogen, it's going to be completely covalent. There's a word for that, where they overlap their valence orbitals in such a way that the electrons kind of make an overlap like this. I'll change the color of my electrons to purple so they stand out. And we have two hydrogen atoms there. This can also happen in any of the diatomics. Now, do you remember the story about my fake roommate? H. What are the other elements that are also diatomic? Got it. The lowercase l there. So let's say that I have bromine. Bromine has 7 valence electrons, so I would draw bromine like this. 1, 2, 3, 4, 5, 6, 7. If I was to draw another bromine, I'm going to put it on this side, on the left side, so that I'll show you what I mean. I'm going to put this bromine on this left side here. So that I can match up where I have that empty hole. And I'm going to go ahead and put 1, 2, 3, 4, 5. Skip this side, it's already full. 6, 7. Or another way to think of it is that I just kind of flipped it over. But you'll notice with the way that I drew this that the valence orbital of this bromine on the right side and the valence orbital of this bromine on the left side there ended up covalencing. So I ended up with 1 electron from each atom there in between the two nuclei. Now, when we have electronegativities that are equal to each other, they're going to pull equally in opposite directions. So hydrogen's electronegativity is 2.2. So that means that there's going to be a force of 2.2 pulling in this direction and a force of 2.2 pulling in this direction. So that means that overall, there's going to be no difference here. Same thing goes for bromine. Bromine's electronegativity, let me just look this up, I don't know it off the top of my head, is 3.0. So a little bit stronger than hydrogen, a lot more protons there in the nucleus. So it's going to be 3.0 in this direction and 3.0 in this direction. So that's also going to end up adding up to 0. There's a term for this. There's a word that we use that's called nonpolar. And nonpolar means that it doesn't have opposite sides. So we're going to learn about this term polar. Polar means that there are two opposites. Nonpolar means that there's no difference all the way around. So it's symmetrical. And those force vectors are canceling each other out. They're adding up to 0. The electrons are at equilibrium between the nuclei. All right, so electrons can be shared either equally, like we see above, or unequally, oops, it's over here, unequally between nuclei. When they're shared equally, we just talked about this, there's a term, and that term is called nonpolar. When they're shared unequally, we call that polar. Now, the reason why polar gets the name, it seems counterintuitive, it seems backwards, right? The reason is because things that are polar are lopsided and end up with a difference in charge, and that makes them stick together and give them special properties. Things that are nonpolar don't end up with a charge and a charge difference and end up not sticking together, so they spread out. So that's how we ended up naming the thing that does something cool and sticks together. All right. If you need to pause the video at any time to write this stuff down and then listen, absolutely go ahead and do that. When both elements have relatively large electronegativities, they will overlap their valence orbitals in order to obtain an octet. So you see that in the bromine example. I'm going to actually scroll back up. You can see that in the bromine example up here. What you'll notice there is that in this bromine molecule, this bromine molecule here, there, what you'll notice is that the valence orbitals are overlapping, and they're doing that so that they can achieve an octet. They normally only have 7 valence electrons, but by overlapping and sharing an electron with each other, they both become stable, and that stability is found in the octet. So when you overlap of your valence orbitals, we call that covalencing. They cooperate, they work together. But this sometimes does not happen equally. Sometimes there's a difference. There's 2 different elements that are bonded to each other. And when that happens, we can have the stronger atom will pull on the electrons more, therefore sharing is not always equal. So when you have 2 different elements, the stronger atom will pull on the electrons more, therefore sharing is not always equal. Blank is a measure of how strongly an atom pulls on an electron in a bond, the force by which, or the attraction for electrons. What is this term? You got it, electronegativity. So electronegativity is a measure of how strongly an atom pulls on electrons in a bond. And you saw up above in that example that when they're the same and they're equal, that bond ends up being perfectly covalent or nonpolar. When there's a difference in the electronegativity, we will end up having all of the electrons on one side in a lopsided compound. So let's look at 2 examples. The first example we're going to look at is Cl2. The second example we're going to look at is HCl. Cl2 is diatomic, and therefore it will be nonpolar. HCl is made out of two different elements, so it's going to end up with two opposite sides within its two different elements. And therefore, it's going to end up with a polar bond. You'll notice that I picked two compounds that only are made out of two atoms, therefore they only have one bond to examine. So when we take a look at Cl2, I'm going to go ahead and draw my Cl, and then I'm going to say 1, 2, 3, 4, 5, 6, 7 valence electrons. If I draw another Cl, I'm going to draw it right next to it so it can use this open spot for sharing. And I'm going to go ahead and go 1, 2, 3, 4, 5. Skip this side, it's already full. 6, 7. That's an example of a nonpolar bond. That's different than HCl on this side. In HCl, I'm going to draw Cl first. And Cl has 1, 2, 3, 4, 5, 6, 7 electrons. You'll notice that I'm going to put my hydrogen on in the same spot where that open spot is. I'm going to draw my H, making sure my font size pretty much stays the same. And then I'm going to go ahead and draw my 1 valence electron for hydrogen, which is going to go between the two nuclei. So you'll see that the polar has what we call opposite sides. So we get that term polar opposites, where this side is going to end up with a partial negative charge because all of the electrons are around the chloride. And this side is going to get a partial positive charge because hydrogen, your nucleus is showing. You know, hydrogen is just a positive nucleus and 1 valence electron around an orbital. The valence electron is over to this side. The side that's exposed on the HCl molecule is going to be positively charged, right? Because we have the Cl, it's much bigger, and it's going to be sharing its electrons, right? 8 around. So where they overlap here is going to be where the covalence occurs, and you'll see that it's very lopsided in its size. All right, the chloride has all the electrons around it, where the hydrogen has no electrons around it.